Hello and welcome to Terminal Unit Sizing. My name is Randy Zimmerman and I'll be your instructor. I'm a chief engineer at Titus and I've worked here for 38 years. I've spent much of that time developing terminal units and serving on numerous committees at ASHRAE and AHRI where terminal unit standards are developed for the HVAC industry. Let's take a look at what we're going to cover today. In order to provide optimal performance, terminal units must be sized and selected properly. It's really not that difficult if we follow a few basic guidelines. Here are my top recommendations for proper control, operation, and improved performance. We'll look at sizing inlets for both VAV and CAV applications, and we'll look at differences between PSC and ECM fan selections. And we'll look at electric and hot water heating coils. We'll follow up with some sample selections to show how best to apply these tips. First off, we never want to oversize VAV inlets. Unfortunately, some people upsize inlets by one size as their standard practice. This results in larger units, larger ductwork, higher first costs, and can sometimes result in higher noise levels when taken to extremes. It's pretty obvious to most people that a damper that's more open for a given airflow limit will be quieter. The more oversized a damper is, the more closed it will be for a given airflow. This rarely causes issues at design airflow, but it could be a major issue at minimum airflow. A damper that's barely cracked open can create a situation where high velocity air is jetting around damper seals. This can create annoying pure tone noise that can often be heard by occupants. This situation cannot be predicted by selection software because the exact tones generated are dependent on too many factors like duct roundness, seal condition, and the exact inlet pressure being applied. The best way to avoid this is to follow a few simple guidelines when sizing VAV inlets. When sizing VAV inlets, the first thing to consider is the design airflow being specified. This is the maximum cooling or heating airflow required to condition a zone on a design cooling or heating day. In our industry, it's standard practice to limit duct velocities to no more than 3,000 feet per minute. This is done in order to prevent possible issues with air erosion to exposed internal lining materials. Most manufacturers publish airflow ranges for terminal units up to a maximum inlet velocity of 2,500 feet per minute. In order to keep sound levels and pressure drops low, VAV inlets on all types of terminal units are best sized for a maximum inlet velocity as close to 2,000 feet per minute as possible without going over by much. We know that air moving at no more than 2,000 feet per minute should not self-generate noise and ductwork, and by keeping our maximum inlet velocity at this level, we won't oversize the inlet and we'll have good airflow control at turn down. Here are my recommended maximum air volumes by inlet size. By observing these maximum airflow limits, you can be sure that the pressure drops and noise levels will be kept as low as possible. Now let's look at the minimum recommended airflows by inlet size. How are these minimum recommended airflows determined? The minimum recommended airflows are the airflows that a manufacturer believes can be controlled within plus or minus 5% accuracy with a factory calibrated controller. For many years, these minimum airflows were based on an inlet sensor signal of 0.03 inches, That's roughly 400 feet per minute. Of course, it was always possible to control down to full shutoff, but control accuracy is reduced as inlet sensor signals get smaller and more difficult to read. In recognition of the vast improvements made by digital control manufacturers with regard to airflow control, many manufacturers now base their minimum recommended airflows on an inlet sensor signal of 0.01 inches, which is roughly 250 feet per minute. Not to be outdone, some manufacturers are now using inlet sensor signals as low as 0.005 inches, which is roughly 175 feet per minute. This seems a bit reckless because all manufacturers are using the same or similar controllers with the same accuracy limitations. Here are the current recommended minimum air volumes by inlet size. We know that we are still slightly conservative in our recommendations, but we think it's the better way to go. So now let's pull it all together. If we have recommended minimum and maximum airflows for a given inlet size, then we have established recommended ranges for VAV inlets. So now let's look at a typical selection. It's been determined that the design cooling requirement for an interior zone is 650 CFM, and the minimum ventilation requirement per ASHRAE 62.1 is 100 CFM. Looking at our variable volume airflow range chart, we can see that an 8-inch round inlet would be ideal. It has a range of 90 to 700 CFM, and we need 100 to 650 CFM, so this is a very easy choice. This selection provides a low pressure drop, low sound levels, and excellent controllability with an 85% turn down. Sometimes we use terminal units to control constant air volume. This is often the case when sizing inlets for critical environment applications like operating rooms, laboratories, or clean rooms. Since there's no turn down to take into consideration, it's possible to oversize these units in order to reduce sound levels and pressure drops. It's still recommended to keep the inlet velocities in a range from 1,000 to 2,000 feet per minute. Here are the recommended constant volume flow ranges by inlet size. So now let's look at a typical selection. It's been determined that the constant volume airflow requirement for a lab space is 1200 CFM per ASHRAE standard 170. Looking at our constant volume airflow range chart, we can see that a 12-inch round with a range of 785 to 1570 CFM could handle it, but we also have the option of upsizing to a 14-inch round with a range of 1070 to 2140 CFM for a slightly lower pressure drop and sound levels, if that's important in this application. Don't try and move too much air with a single terminal unit. Generally speaking, the more air you move, the more noise you'll make. And since a terminal unit typically defines a temperature control zone, there's often the risk of creating comfort issues when zones become overly large. Often larger spaces contain both perimeter and interior areas. It would be therefore better to use separate smaller units to handle these areas. As far as single terminals, I rarely see a need to use a unit with an inlet larger than a 16-inch round. Although larger inlets are available, the only suitable applications usually involve large spaces like gymnasiums and industrial applications. As far as fan-powered terminals, it's generally a good practice not to move much more than 2,000 CFM through a single unit. Although there are units available that can move in excess of 4,000 CFM, they usually have large dual blowers and tend to create a concentrated noise source above the ceiling. From both a noise and comfort perspective, it usually works out better to split the zone and serve it with two smaller units. Tiny fan terminals don't make sense, but I'm often asked about them. Questions like, why don't you have a series fan terminal that can operate as low as 100 CFM? Actually, we do. Our DTFS size A with ECM can go as low as 75 CFM with a 1/4 inch downstream static pressure. On some models, it's necessary to go to a low-profile version of a model in order to get to the lowest fan airflows. Just because we offer them doesn't mean that they're recommended. I mean, what's the point of putting another fan in the ceiling if it's only handling such low air volumes? Do you really need a fan unit over every closet and vestibule? Spaces like these are probably best handled with small single-duct VAV terminals. Now let's look at fan selection. The way we select a fan depends on the type of motor we're using. Permanent split capacitor, or PSC motors, are the older type that are being used less and less. The newer electronically commutated motor, or ECM, has many advantages and improvements over the PSC motor. PSC motors typically have sleeve bearings, a speed range of 600 to 1075 RPM, an efficiency range of 20 to 60%, and a service life in a series fan application of 10 to 12 years. These motors use silicon-controlled rectifier, or SCR, speed controls to adjust fan motor speeds. Although industry classifies these motors as high efficiency, that's really only in comparison to older shaded pole induction motors. The biggest PSC problem generally concerns the SCR speed controller. It basically takes the smooth AC sine wave power and chops and notches it to reduce the useful power going to the motor. That's why some people refer to them as wave choppers. When reducing fan speeds in this way, several things happen. First off, the efficiency begins dropping from 60% to 20%. Second, the motor reacts to the distorted power input by running hotter and often producing an audible low-frequency humming noise. Unfortunately, this hum goes straight through typical lay-in ceilings because they're designed to block and absorb higher frequency sounds. The higher operating temperature tends to reduce the service life, and if the motor speed drops below 600 RPM, the bearings will cease to properly lubricate, resulting in rapid wear and premature failure. ECMs are quickly taking over the industry. These are programmable motors with ball bearings, a speed range of 300 to 1200, a minimum efficiency of 70 to 80%, and a service life in a series fan application of 20 to 30 years. These motors take AC power, internally rectify it to DC, and pulse DC power through an internal digital controller. They use pulse width modulated, or PWM, speed controls. ECMs have none of the problems of PSC motors. Speeds can be adjusted between programmed minimum and maximum fan curves. The ball bearings have no minimum speed limit, and the PWM speed controls don't create any power distortion. Something very important to note is that ECM efficiency actually increases as speeds are reduced, and efficiencies of over 90% are easily achieved. Energy codes are impacting which motors must be used in various applications. Applications that have a fan running during cooling are generally required to have a minimum efficiency of 70%, requiring the use of an ECM fan. Applications that only run the fan during heating are generally still able to use PSC fans. Here is a typical PSC fan curve. You can see that it has the CFM going up the vertical axis and the discharge static pressure on the horizontal axis. The top curve is for a unit with no coil or an electric coil. Then there are two curves for a 1-row or a 2-row water coil. The lowest curve is the dreaded 600 RPM minimum curve that we want to stay away from. PSC fan motors should be selected near the top of their operating range to get the highest efficiency and the longest service life. This generally means in the top 25% of their range. Now don't select at the very top of the curve because there needs to be some headroom available for field balancing adjustments. An ECM fan curve is set up similarly to the PSC curve, but it looks a little different. The ECM curve is usually quite flat across most of the fan range because the ECM is a smart motor. Most manufacturers program them to automatically correct for external changes to hold the airflow volume constant. Eventually, the ECM runs out of power and then the curve noses over. ECM should be selected in the lower portion of their operating range in order to get the very highest efficiency and the quietest operation. This generally means in the bottom 50% of their range. When heating from overhead diffusers, it's critical that the leaving air temperatures are limited. Although UL safety standards allow discharge temperatures from electric coils as high as 120 degrees Fahrenheit, ASHRAE Standard 62.1 recommends that overhead heating temperatures should be no greater than 15 degrees higher than the desired room temperature. Failure to observe this limit will result in increased minimum ventilation requirements to maintain zone ventilation effectiveness. By limiting leaving air temperatures, thermal comfort is improved through reduced floor-to-ceiling temperature stratification and increased room air mixing. So exactly how do we limit our leaving air temperatures? It's pretty simple. We look at the scheduled total heat capacity of the coil to determine the heating airflow rate required to keep the discharge temperature within 15 degrees of the room temperature. The delta T is going to be the temperature rise of the coil. So we've got two equations here. We've got CFM equals MBH times 927 divided by delta T. Or for electric coils, we've got CFM equals kilowatts times 3160 divided by delta T. So let's look at an example. An electric coil is scheduled for 3 kilowatts with 55 degree supply air and a desired room temperature of 72 degrees. We need to keep the discharge temperature so that it doesn't exceed 87 degrees Fahrenheit. So if we look at our equation, CFM equals 3 times 3160 divided by 87 minus 55, and the result is going to be 296 CFM. As far as hot water coil selections are concerned, there are a few things to keep in mind. First off, it's nearly impossible to get an exact match to a schedule unless your units were the basis of the design. Equipment schedules often provide too much information when it comes to water coils. Rather than specifying every minute detail of performance, it would be better to simply concentrate on the job at hand namely providing the necessary heat. The only way to get an exact schedule match would likely require a custom coil design for each line of the schedule. Obviously, this is prohibitively expensive. The best way to schedule hot water coils is to schedule the MBH or leaving air temperature required with some limits on the maximum allowable GPMs and water pressure drops. The most troublesome schedules are those that have firm requirements on leaving water temperatures or odd requirements regarding water velocities. Requirements like these often lead to a custom coil solution and much added cost and lead time. Current trends towards condensing boilers have resulted in lower supply water temperatures. Rather than 180 degree water, we're now seeing temperatures as low as 100 degrees. Rather than add more and more rows, the best solution for single duct units is to select an enlarged casing option. This puts a smaller inlet on a larger casing so that we get a larger water coil. Increasing the fin area is the best and least costly way to deal with low water temperatures. There are a few things to consider when selecting electric coils. The first thing is whether the coils will be staged or SCR. Although modulating electric coils no longer use SCRs, this term has become the generic description for modulating heat. The next thing involves the total heat capacity of the coil. If the kilowatt rating is too high for the scheduled airflow rate and supply air temperature, the leaving air temperatures will be excessive. Although we recommend not exceeding a 15 degree delta T per ASHRAE 62.1, we know that leaving air temperatures above 100 degrees can cause intermittent heater operation and will eventually prematurely burn out the elements. So beware of low airflows and oversized heaters. It's also important to note there are limits on how low the heat capacity can be on an electric coil. As element voltages and phases increase, the minimum kilowatt also must increase. This is due to the fact that as voltages increase and kilowatts decrease, the element wire diameter must get smaller. At some point, the wire becomes so fine and brittle that it will be fragile and result in an unreliable and short service life. I'm often asked to provide 480-volt three-phase heaters as small as 1 kilowatt. This isn't possible for us to build as our minimum design goes down to 2.5 kilowatts, but it really doesn't make sense anyway. 480-volt three-phase electrical circuits must use heavy-duty 600-volt components, including breakers, wire, conduit, etc. The breaker will occupy 3 slots in the breaker panel, and the current draw of that 1 kilowatt heater would only be 1.2 amps. That doesn't make sense. A better choice would be a 277-volt, one-phase, 1 kilowatt electric coil. So I've tried to provide some practical guidelines for sizing and selecting terminal units. Hopefully these tips will lead you to better selections and let you know when a schedule looks like trouble. Sometimes I break my own rules to make things work, but that's typical of the challenges we all face. It's really a matter of finding the unit that can handle the primary air, fan air, and any heating options and do it all in the very best way. That often means striking a balance. Then there are all the other compromises that must be made in terms of budget, space limitations, sound levels, and other considerations. Sometimes this process seems more like an art than a science if you're doing it right. To summarize what we covered today, always size VAV inlets for 2,000 feet per minute. We have some flexibility with CAV inlets, but keep them in the range of 1,000 to 2,000 feet per minute. Select PSC fans in the top 75% of their range. Select ECM fans in the bottom 50% of their range. Limit leaving air temperatures to a 15-degree delta T to meet ASHRAE 62.1 requirements. Select water coils to meet leaving air temperature and MBH requirements without exceeding maximum GPMs by too much. And enlarged casings are the best way to mitigate low water temperatures. Thank you for attending this webinar. I sincerely hope that it's improved your understanding of terminal unit sizing and that some of these concepts that we covered will help you in your future ventures.